Apache Cassandra can serve as both the real-time data store for online transaction processing as well as the read-intensive database for data warehousing operations. In order to combine these two use cases into a single database, Apache Cassandra required lots of innovation. In today's episode of Software Engineering Daily, we discuss the internals of Cassandra. Tim Berglund takes us through how Cassandra performs reads and writes, and how Cassandra offers tunable consistency. We also discuss what inspirations Cassandra took from the Amazon Dynamo paper, as well as the Google BigTable paper. But first, a word from a sponsor that helps keep Software Engineering Daily fault-tolerant. As a software engineer, you have tremendous leverage in the employment market. Every company needs software engineers, and these companies are all competing for you, the engineer, a scarce resource. But as an individual engineer, you don't have much insight into this incredibly opaque market. That's where Hired.com comes in. Hired.com assigns you a talent advocate who works to understand your needs and works to find you the perfect job. Go to hired.com/SEDaily to try out the platform today and get a $2,000 bonus if you find a job. The companies on Hired compete for you, the engineer, and they make bids to win your talent. These are companies like Facebook and Uber, companies that we know are on the cutting edge of engineering because they've come on Software Engineering Daily to talk about their tech stack. I've used Hired personally, and I've experienced firsthand the ease of finding a well-paid, enjoyable job. This was way better than replying to LinkedIn messages from uninformed recruiters, and it was also certainly better than using a job search engine. To find a great job and support Software Engineering Daily, go to hired.com/SEDaily and get a $2,000 bonus upon finding a job. Check it out. It would support the show. Now let's get on with the show. Tim Berglund is an engineer with DataStax, a company that develops and provides support for the Cassandra database. He will be hosting training sessions for Apache Cassandra at the upcoming Strata plus Hadoop World in San Jose, and Apache Cassandra will be the focus of our conversation. Tim, welcome to Software Engineering Daily.
Thanks, Jeff. It's great to be on the show. And I should say, technically, I'm not an engineer for DataStax.
Okay.
So what I'm going to do is get rid of all my credibility with your audience right up front. Mostly, I'm a manager. Now, I do write code, and I am responsible for a lot of training materials. We'll talk about that. I certainly have a background as a developer, but I don't work for DataStax as an engineer. We still have lots of cool stuff to talk about, though, so don't worry.
Absolutely. Okay, well, we'll consider that an eventually consistent introduction.
Exactly.
So with that in mind, what is Cassandra?
All right, great question. Cassandra is a distributed database. That's probably the simplest way to think about it. If you like the term NoSQL, then it definitely fits into that category. It's one of these non-relational or post-relational or databases that happen not to use a relational data model. And in that universe of databases, there's, once you go outside the relational camp, there are a couple of characteristics I think are helpful to think about. One is, are you built for scale or not? Cassandra, absolutely. Cassandra is built for scale, period. And in terms of data model, it has what I would describe as a tabular data model. It presents in a very familiar way to a relational developer, kind of looks like the relational model is kind of winking at you. It's not relational, but you store data in rows and columns, and there are data types and select queries and insert queries and things like that.
And Cassandra can serve as both the real-time data store for online or transactional applications. It can also serve as the read-intensive database for data warehousing operations. You kind of touched on this in terms of the data model, but how does Cassandra achieve this combination of features where it can exist as both the real-time data store and the read-intensive database for data warehousing?
Great question. So, yeah, give me a minute on that one. That's you kind of pressed a button there. There's a lot to talk about. Now, Historically, and you heard this more in the early days of Cassandra 4 and 5 years ago, but Cassandra has always been thought of as a database with amazing write performance. And the downside of that's cool, by the way, because usually writing is a lot harder than reading in a database. That's always true in relational databases. So that's kind of neat and a curiosity, and gives you access to lots of applications you couldn't use to build things with otherwise. The downside of that is people have kind of taken that to mean, well, it must be slow, it reads. That's not really the case. But let's kind of take the write performance first. The secret to the write performance has to do historically with the fact that when you zoom into a particular node in this distributed database that's taking writes, there's under the covers a thing called a log structured merge tree. And really what that means is writes get batched up in memory for a short period of time and then written out sequentially in these immutable data files. So everything about that write path is aligned towards getting the best performance out of the I/O subsystem possible. You're never, for example, seeking to a place on disk and changing something in place and then moving on. You're always doing this nice, fast sequential write. So that's how you get the fast write performance. Now, read performance, on the other hand, sort of comes out in the wash. You still end up getting real high performance read performance. What you don't get, you said using Cassandra as a data warehouse. What you don't get out of this system is real flexible ad hoc reads. So if you want truly ad hoc analytics on top of your transactional data, you're going to layer some other kind of system on top of the Cassandra data. And historically, the answer has been Hadoop, and more recently, the answer is Spark. We've done some interesting things in the training department with respect to running Spark on curriculum. And I've got a 90-minute conference talk I do where I live code a little Spark application on top of Cassandra data. But that's the answer for the ad hoc stuff.
Oh, okay. So I'd love to get into the Spark stuff eventually, but let's keep talking a little bit more about the core of Cassandra. Cassandra was inspired by both the Amazon Dynamo paper and the Google BigTable paper. So I'd like to talk about the inspirations that it took from each of these. But first, what did Cassandra take away from Dynamo?
Great question. Basically, it's the way it functions as a distributed system, the way it spreads data around the various nodes in a cluster, it gets from Dynamo. And if you back up a step and you think, well, look, I'm going to be a distributed database, one of the primary problems I have to solve is I have to decide how to distribute things. I've got too much data to go in one place. So how do I know where I'm going to put it, on what nodes I will put it? The basic insight in Dynamo was something like this. Dynamo, the data model, was a hash table. Dynamo is properly a distributed hash table. So the data model is a key and a value. And what Dynamo said is we'll take the key and we'll hash it. And then we'll take the output of that hash function, mod the number of nodes in my cluster. So say I've got a 10-node Dynamo cluster. I have some 160-bit hash function output. That number mod 10, and that's the node that I'll write that key to. Likewise, when it comes time to read, I read a key, I hash the key. I mod that hash function output by the number of nodes, and that tells me what node I go to get the stuff from. And that's just in a nutshell distributed hashing. And Cassandra gets that from Dynamo. Now, I should mention, if you have just freshly read the Dynamo paper, and then you go watch like some of the online training my team has done on how Cassandra does that, they're a little different. But in spirit, they're really the same thing. And that's clearly the influence of Dynamo on Cassandra is the distributed hashing.
So the distributed hashing, or it's also sometimes called consistent hashing, have there been any methodologies or tactics around distributed hashing that have evolved since the time of the Dynamo paper?
Yeah, there's been. I don't know that I would say evolved. One example, a feature that has come in Cassandra. No, it would be fair to call this evolutionary. A feature that's entered Cassandra. Let's explain the basic template I just gave you for how distributed hashing works. Let's just start with that and say, well, that's cool. I'd like that database, and I just I made up a number and I said I had a 10-node cluster, which is great. But ideally, like your application succeeds and customers like your thing or whatever it is you're doing, and it grows, and then you need to add more computers, right? You've got too much work, too much data, and you need to expand. And you'd like to be able to do that without like taking the cluster down. I mean, there just isn't, scheduled downtime isn't really a thing that you can design into a system anymore. So those were nice days, but they're gone. So to grow that cluster, you would insert a node in between two other nodes, right? Well, that new node has to get its data from somewhere, and it's going to be from its neighbor in this hash ring with the way Cassandra works. And so what you're going to do there is you're going to say, well, Mr. Neighbor node, you've got 3 terabytes of stuff, and I need 1.5 of them. And I know you're busy being a database right now, and the network is doing all these other databasey things, but I just need to saturate you for a little bit and take your 1.5 terabytes from you before I can actually enter the cluster as a new node. That's in that naive consistent hashing scheme I described. That's how it works. And you can do that. Okay, that's not like it's fundamentally broken. You can throttle the data rates and all that kind of stuff. But a feature that Cassandra has grown is something called virtual nodes or vNodes. And basically what that means is, instead of saying, if you could just imagine a ring, this is a podcast, so I can't draw you a picture, but imagine 10 nodes drawn in a circle. And imagine my hash code space is 1 to 100. And so, the first node takes hash codes 0 to 9, and then the next one 10 to 11, and so on. You're 10 to 11 to 20, and then 21 to 31 in that circle. vNodes break up that ring such that each individual node is acting like it's taking a bunch of slices of that ring from all over the place. In other words, instead of just one sector of that circle being allocated, that hash ring being allocated to a given node, that node randomly has many small sectors from all around the ring. What that means is when I go to add, it actually has a lot of implications, but in terms of growing the cluster, when I go to add a node, now instead of saying, hey, Mr. Neighbor to the right, you need to stream 1.5 terabytes to me, every node in the cluster gets to split that work. So I get 1.5 terabytes divided by 9 from all of the other nodes in the cluster. And it's still network traffic. It's still a thing that takes finite time, but the whole burden is not placed on one node. So vNodes would be an example of a little tweak on consistent hashing that Cassandra has developed along the way.
Okay. That's great. Yeah. And I think consistent hashing is a really interesting and important topic. And we explored it in a couple previous episodes. There was a show about React recently, and then also there's a show before that about the engineering at Uber, and both of those talked about some some other additional ways you can use consistent hashing. So it
really shows up all over the place. Is the funny thing.
Oh, it does.
Like if you look at how Kafka works, it's kind of in there. And this is to a first order approximation. Anytime you got lots of stuff and you need to put it in lots of places, right now it seems like the answer that human beings have for computer programs to do that is consistent hashing. So.
It's funny because I didn't know about it until, I was like at least 100 episodes into doing this show before I knew I didn't know about consistent hashing. Yeah, so at least in terms of a distributed system, but it's like core to modern distributed systems.
It really is. And that's the advantage of doing the show. So
absolutely. So, okay, with that in mind, okay, we've discussed the implications of the Dynamo paper on Cassandra. What about the BigTable paper?
Got it. So, BigTable has lent some terminology that kind of sneaks in here and there that isn't super important. But the thing that is important is the data model. Cassandra gets its data model from BigTable. Now, must proceed with caution here because it used to be true prior to, Cassandra 0.6, that the statement I just made was uber meaningful. Like if you knew the BigTable data model, you knew the Cassandra data model, and you were off to the races. These days, the way the API that Cassandra presents itself to developers is the Cassandra Query Language, or CQL, this tabular data model, and this incredibly SQL-like query language that's super easy to learn, super easy to use because it's based on stuff you already know. And so this Cassandra gets its data model from BigTable thing doesn't feel like it matters as much anymore. Now, there is this underlying storage model that you have to understand if you're going to be good at Cassandra, and that's the thing. We call that the storage model now, and it comes from BigTable. And if I could just briefly describe that.
Please do.
Yeah. You have data that's organized into tables. There they are. They're tables. They're these named things. And a table is, in BigTable, a hash table of hash tables. All right, you've got one thing called the row key, or in Cassandra, we call this the partition key now. And that uniquely identifies a row in your table. And inside that row, in BigTable terms, is another hash table. So that's the BigTable data model. That's the underlying Cassandra storage model. And it's important that you know that for purposes of kind of boundary checking your data model when you model in CQL. But that abstraction is no longer a faithful abstraction with which to think about programming Cassandra. So it's a tool, but you want to make sure that you don't, like if you say hash table of hash tables, 4.5 years ago, 5 years ago, that was very meaningful. And I spoke those words when I talked about Cassandra. If you say that now, my antenna go up. I'm like, whoa, what are you even talking about? That's not really what it is. It is under the covers. You just have to know that that's the under the covers look.
Okay, well, I mean, I do like this show to prioritize the under the covers look. So let's delve into that data model a little more, given that it is still faithful under the covers. And so, you called it a hash table of hash tables. As I understand, Cassandra is a hybrid between a key value and a column-oriented database. Can you explain this way of looking at it?
I can. And in the process, I want to talk you out of that a little bit. So,
please do.
It's funny. Just last week, I was having this conversation about the column-oriented data. It historically has fallen into the category of so-called column family databases, and that is its BigTable lineage. And like I said, that's true at the level that data is getting stored on a node, and it's important for you to know that. And here's why it's important. You know the hash table of hash tables I described? If you just think of it as the first hash table, okay, forget about the nested hash table. That's just the value. Whatever that.
So this is the partition, the hash into a partition.
Exactly.
So is this like a single server that you're hashing into?
No, we're cluster wide here. Cluster wide.
Okay. Cluster wide partition.
So
got it.
Kind of back off, blur your eyes a little bit, and say a table is a hash table. It's got a partition key and then this value, and we're going to be intentionally ignorant of the structure of that value for a moment. And so a table is just this unordered bag of all of these key value pairs. So in that sense, it's worthwhile to talk about Cassandra as a key value store. In fact, you can find video of me on the internet describing Cassandra at conference talks, and in fact, our own training materials that my team makes. Early on in describing how Cassandra works as a distributed system, I always talk about it as a key value store. So it's not one, but that's at that level of the table. The partition key is the key, and then there's this value thing. And I say that's an unordered bag of key value pairs because the partition key gets hashed, and that's how we decide what node that partition is going to live on, node or nodes that partition will live on. So you've got that. In that sense, yes, Cassandra is to a not even a first order approximation, but like almost a first order approximation. It's like a key value store. Now, let's dive into the what's inside a partition thing. At the storage engine level, or the in historical terms, what we used to call the thrift API, and what some people still call the thrift API level of the data model, the value in that hash table inside that partition, that's again another key value store. That's the embedded hash table. Now, the thing is here's why it's important for you to know about this. That outer hash table, the partition key and the value, that thing, there can be arbitrarily many of those. If your table gets too many rows or too many partitions to it, add computers to your cluster. It'll be okay. You can't realistically make that too big. The inner hash table, at this low level thinking here, that can get too big. And if you put, 100,000 or 1,000,000 key value pairs in there, you might start to regret putting more. So at that level, that detail is important. And when we get up to the programmer level of using CQL and creating a data model, then there are some things that, some reasons we're going to have to know about that inner limitation.
Okay. Well, so without spending too much more time on the data model, I guess we can zoom out and maybe we'll come back to the data model and touch on it in other topics. But so Cassandra was built from the ground up with an understanding that hardware failures can and do occur. How did this affect the construction of Cassandra?
Good question. Well, Cassandra had already decided to be a distributed database. The assumption was, again, I've got too much stuff to put in one place, or one thing can't be reliable enough, so we're going to move our data, we're going to have our data spread among many computers. So enter consistent hashing, basically, and that whole mechanism. So you're kind of there already. But the system I described when I was describing consistent hashing earlier sounded kind of cowboy in that there was only one copy of anything. And of course, that would be bad because, any of those computers, any of those disks, all that stuff might die. So Cassandra has built-in replication. If you're going to put data on a node, then you get to decide other nodes. You have an algorithm that decides in a systematic way, what are the other nodes in the cluster where I'll store a copy of that data. So I've got it in, say, 3 places at once. And easy enough, right? You could imagine, come up with some mechanism that says, well, the data goes on node 4, and so I'll put a copy on node 5 and node 6 as well. And that's great. But actually, life is terrible again now because you have all of these decisions to make, like, what if I can only write it to 2 of the computers? What if I can only write it to 1 of the computers? Is that a successful write? And then later on, when I go to read it, what if the nodes disagree? How do I figure out systematically which of the nodes is correct? So things like that are all built into Cassandra. And what I love about it, actually, I love the decisions Cassandra made there from a design perspective, because the developer is in the driver's seat for all the right things. You get to make the decision. I said, what if 1 node is down? What if 2 nodes are down out of the 3? Is that a successful write? Well, hey, that's up to me. I'm the developer. I'm going to make the decision about I'm going to make an intentional trade-off as an engineering decision here. How much consistency do I actually need and when? And how much reliability do I need? And what kind of latency do I need on this write? All of those things are going to be determined by how many copies I need before the write can move on.
So I think you're talking about the term tunable consistency.
This is exactly what we call it. So
why and how can we explore the different axes of tunable consistency?
Well, I think of there being 3 axes. One of those are 3 dimensions. One of those dimensions is pretty small in that it's not really the thing that usually comes up as an engineer building something on Cassandra, but it's there for real. So the primary trade-offs that we're making are consistency and latency. All right. So the more nodes I'm going to require in a write, like say, let's just always assume for purpose of discussion that our replication factor is 3. We want 3 copies of the data. Well, it's a theoretical possibility that I could say I need all 3 copies, all 3 nodes to write successfully, to take the write before I move on. In practice, nobody does that because that's completely intolerant of any failure. So usually with a replication factor of 3, the trade-off that's being made is, do I need 2 or do I need 1? And what I'm getting there, if I say, look, I only need one node to succeed, then I will see better latency numbers. My writes will appear to complete. They will complete more quickly than if I need to write two nodes successfully when I write. So usually in the mind of the engineer or the architect building that system, they're saying, I need the latency, so I'm going to give up consistency. We're trading latency for consistency. And briefly, go ahead.
No, go ahead.
Briefly there, same thing on the read. I can say, hey, I'm reading and I know three of you have this data. Whoever is going to give me the answer fastest, I'm going to take it from you. I can do that. Or I can say, I would like two of you to answer and agree on what the right answer is. Again, I'm trading consistency for latency. And here, in brief summary, is the magic. When I write with the consistency level called quorum, that means more than half of the nodes. In other words, replication factor 3, I need two nodes to take the write for me to write. And then when I read, I need two nodes to agree on the answer when I read. If I do that, or not even agree, but I need them to respond. If I do that, then I'm guaranteed I'll always read my writes. I have a strongly consistent database. So this whole thing about eventual consistency, it's strongly consistent if I write and read with quorum. It's not eventually consistent. It's just as consistent as a single server relational database. Now, those are slower writes and reads. So that's basically the trade-off that I've made. If I write with one and read with one, quickest node to answer in both cases, then that is an eventually consistent system with lower latency. The tiny dimension is reliability. So given that nobody ever really requires a whole replica set to read and write, that would be extremely unreliable. I'm slightly more available or reliable with a consistency level of 1 and slightly less available with 2.
So these axes that you discussed are consistency, latency, and reliability.
Yeah, or availability would probably be a better thing for me to say. I said reliability, but I should say availability.
Okay. Well, I was going to say the trade-offs that we often hear about are the ones that are outlined by the CAP theorem.
Yes.
Consistency, availability, and partition tolerance. So if I'm understanding correctly, maybe the things that you're talking about are maybe a more updated vocabulary version of the CAP acronym. Would you say that's accurate?
No, I wouldn't say that. No.
Or is it, okay.
I would say that the claims of the CAP theorem are absolute, and they are claims on the nature of reality. Okay, just given the strength of the proof, it seems like it's not, the proof of the theorem doesn't seem like it's really under any threat. It's kind of like, okay, the laws of logic say this about reality, and this is the one reality you get to have, so deal with it. Given that, the CAP theorem is saying, pick any two of these three desirable utilities of your distributed database. Cassandra is a distributed database, therefore it doesn't really get to choose whether it's partition tolerant. Okay, it would
right.
be a completely unsuccessful product if it didn't. So I have to be partition tolerant. Now I have decisions to make about consistency and availability. Those decisions remain, and those claims are all true. What I'm saying is, from an implementation perspective, like the CAP theorem doesn't say anything about latency. That's not a thing that participates in the argument of the theorem. But in reality, that is a thing you trade off. So it comes more to the fore of the mind of the engineer trading consistency versus latency than consistency versus availability is kind of practically how that works out. The availability trade's still there, but it doesn't seem to get pride of place in the trade-offs.
Engineers love automation, and Wealthfront automates your investing. As a software engineer, there are certain processes that you want to execute no matter what, like integration tests during a build. You wouldn't execute integration tests manually. You would use a continuous integration tool like CodeShip or Jenkins to automate your integration tests. Wealthfront is a tool to automate investing. Just like a continuous integration tool runs your tests automatically, Wealthfront can reinvest your dividends automatically and perform tax loss harvesting automatically. To get your first $15,000 managed by Wealthfront for free, go to wealthfront.com/sedaily and get started with Wealthfront's layer of automation on top of your portfolio. Wealthfront.com/sedaily. Check it out. It would support Software Engineering Daily, and you will get $15,000 managed for free if you sign up. Automate your investing. Get back to the things that you can't automate, like writing code. So these systems are often having different proportions of reads versus writes. How can Cassandra be tuned for different, with this tunable consistency in mind, with different ratios of reads to writes?
Good question. Okay. And that doesn't come up so much in the tunable consistency end of things.
Okay.
But it is a real thing. And this is like a practical implementation issue. When you build a database this way, you find that certain schemes work better for read-heavy workloads and certain schemes work better for write-heavy workloads. And I don't know, maybe if you ask somebody else, you could get a different view here. But when you say that, you say, I've got a read-heavy system, I've got a write-heavy system, that calls up a different process in Cassandra, which is another really neat internal mechanism that's kind of fun to talk about, called compaction. And compaction is a fact of life when you decide to be a log-structured merge tree storage engine, like Cassandra is. Compaction is a thing you will do. So the basic, and I mentioned the log-structured merge tree thing before, the basic notion there, when it says log-structured, unfortunately, log can mean a few different things. It can mean a big piece of a tree. It can be short for logarithm, or it can be a record that you append to. And of course, this means the latter. If you think about a log, like a log file, and like I have a Java background, so logging frameworks are a thing we reinvent like every 18 months. It's fun in the Java world. But you have a log file, you write stuff to the end. And like I said, in Cassandra, you never seek into the middle of something and try to change it. And if you think this is a log, and if you're editing something in the middle of a log, it's like you're probably committing a crime, right? If you're editing a log file, something is bad. So logs are things we append to, and then we don't change them. And that's what data files are like in Cassandra. We sort of buffer up writes in memory, and then when we decide we've had enough of that, we'll flush them out into a data file on disk. A data file on disk is called an SS table, which, by the way, is a term that we get from BigTable. And those SS tables, they are a lot like logs, immutable. We can't change them. So what that means is we kind of have a problem. We've got all these immutable things, and we're accumulating them on disk, but we don't have immutable data. The data model lets you change the value of a column in a row, and anything could change. We could delete things. So you end up with a lot of like storage cruft. You've got these old SS tables, old versions of these quote unquote log files that you don't need anymore. And so there's a periodic internal maintenance operation that nodes do by themselves called compaction. So when you talk about workloads that write a lot and workloads that read a lot, this bears on this compaction process. There isn't just one way to compact data. There are a number of compaction strategies, and with every, well, that's not quite true, but occasionally with major Cassandra releases, you'll get a new compaction strategy. So this is an ongoing area of research and optimization in Cassandra, and in any database that's architecturally like Cassandra that people are actually using, this is a thing that you're going to keep working on. You always want it to get better.
Do these compaction strategies evolve in parallel to how garbage collectors evolve?
Not exactly, and like not intentionally. There's clearly an analogy there because you are collecting garbage, but like you look at JVM garbage collectors. They only look like Cassandra compaction strategies if you push it. You wouldn't look at one and say, oh, hey, look, they obviously got that from there. It's more like, well, I have stuff and I don't need that stuff, and this stuff changes a lot, this stuff doesn't change a lot, and then let's make it all better. So at that level, they're the same, but that's about as far as it goes.
Okay. Well, okay. So it's talking in a more, applicable way to the end user. Can you take us through the process of writing to Cassandra? Just like a simple write. What occurs from top to bottom?
Boy, you got it. Okay. Now, let's take it from the language driver. Okay. So we'll start. We'll talk Java because it feels like home to me. And you've got some.
Me too.
Good.
It's an uncomfortable home. Lots of bad memories.
But, it's the only home.
It was an abusive childhood.
It was, but you still go home for Thanksgiving, don't you? Now, there's a query that gets executed against the Java driver in the application, and that query gets sent over a socket on a particular port to where? Well, it's a distributed database. So right away, we've got a weird question to answer. What node are you going to send it to? Well, that driver is able to connect to some node. It needs to start by connecting to some node when the application boots up in the database, and it'll get from that node a list of the addresses of all of the nodes in the cluster. Maybe it's 3, maybe it's 300. It could be changing over time. The driver has to stay up to date, but the driver will load balance for you. So as soon as that query gets sent to the cluster, already the driver has had to make a decision about how to do that load balancing. That's configurable. Like that's a 15-minute topic or 20-minute topic in good curriculum about how all that works. But you pick some dang node in the cluster, you send the query there. That that node has just assumed the role of coordinator. Now, it could have been anybody. There isn't any central node in Cassandra. Every node is a peer. There is no master. There is no single point of failure. But that node, which is just like all the other nodes, has coordinator duty. And of course, what it doesn't know is that all of its comrades in the cluster are probably also coordinating all the time, right? So driver sends query, load balances, sends it to a node. Node says, okay, I'm the coordinator. The coordinator is going to look at the write. You said this is a write. And it's going to say, all right, this is a write to this partition key. Now that partition key is probably going to be, in a lot of cases, it ends up being a UUID. That's pretty common for reasons we can talk about later. So here's this partition key. It's a UUID. And the coordinator says, let me hash that. I'll run it through the hash function and mod the number of nodes. And then it'll say, all right, this is the node it goes to. It goes to node 53. But we're replicating, so it also goes to node 54 and 55. So the coordinator is going to open connections to those three computers and say, I'm going to send it to 53, 54, and 55. And then I'm going to wait. Now, we've got a lot of balls in the air already. The client, we have no idea what's going on there. I haven't said if the client has moved on or is happy or anything. In fact, the client is still blocked on this write. Nothing has moved on. The coordinator's got the write. It's forwarded it to those three nodes. And from the coordinator and the client standpoint, they're all waiting. Now, let's jump over to the nodes that got that write. So zoom in on those guys. Node says, okay, good news. I have a write coming in. For purposes of simplicity, I'm going to ignore any caching that might be happening. There's some caching that could be happening, but just pretend it doesn't.
Sure.
So we won't update any caches here. All right. So the node has to do two things right away. It has to put that in this in-memory structure called a mem table. Before, when I was talking about log-structured merge trees, I said it gets cached in memory. That mem table is that in-memory structure. It's buffering up writes before spooling them off to disk. But it would be kind of dangerous if there were no disk I/O at all. So as it writes to the mem table, it also very quickly appends it to a structure called the commit log. There's very little computation. It's just this append-only thing. Just kind of, there's the mutation event, stick it on the end of the commit log. And as soon as that write succeeds to the commit log, That is, the operating system reports that the disk hardware has done the write. And anybody who knows anything about disks or operating systems or operational things knows there's just layers upon layers of lies that could be happening there. But anyway, Cassandra says, okay, I did the write. It's in the commit log. It's written to disk. It's in the mem table. I will tell the coordinator that I'm done. So that node says back to the coordinator, gotcha, we're all done here. Now the coordinator, this is where the consistency decision is made. If the client said, I want consistency level 1, then as soon as one of those answers comes back, the coordinator can say, hey, client, you can unblock. Your write has succeeded. If it was, in this case, a quorum, then the coordinator would be waiting around for the other write. And when it got 2 writes, it would say, client, you may unblock.
Assuming replication factor 3.
Which is true for all this. All right, almost done. Let's go back onto that node. So, and that really is the write, by the way. But at some point in the future, enough of those writes into this mem table thing, that's in memory, memory will run out, and so that mem table will get flushed onto that disk structure, that immutable data file called the SS table. And that's right. the very end of the write.
Sure. Okay. And, for listeners who want a read walkthrough, I mean, I think a read is fairly simpler, and I think we walked through it in the React episode. I'm not 100% sure, but I'm pretty sure that Cassandra reads similarly to how React does.
I don't think I'm fuzzy on React. It's been about 4 years,
okay.
But the read is actually harder than the write. That's
it is.
The weird thing about Cassandra. Yeah, that's not true of most databases, but it can write faster than it can read because it does less work on write. So let me make this quick.
Yeah, please walk us through that.
So the driver, the coordinator, all that's the same. Okay, the coordinator is quote unquote randomly selected by the driver. It gets the read and it says, okay, I've got work to do. This read is for this partition key. That means, again, we'll say 53, 54, 55, those nodes in the cluster, this random cluster we're making up, and it will forward that read request to those 3 nodes. Now, those 3 nodes will get the read, and I've never done this audio only. I've always had visuals. So let me just simplify this a little bit. Imagine everything you needed. I'm a node, I get that read, and I got this mem table, right? We wrote to that a minute ago. And everything I need in the read is right there in the mem table. I'm like, oh, sweet. Okay, well, take it out of mem table, go. I know that's going to be the most recent data, so that's like an in-memory, quote-unquote, cached kind of thing, and just send that back to the coordinator. So that's the good thing. The slightly more complex situation is if I have to go to disk. Okay, so if I have to go to disk, then I have all of these SS tables that I've flushed in the past. As writing happens, I'm continually flushing SS table after SS table, and that could happen every few seconds or every few days. It just depends on how much write traffic there is and, various configuration parameters. But to keep things simple, if you just imagine this sequence of SS tables, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What I have to do now, if what I need is not in the mem table, I have to go to the newest SS table and look there. And if I find everything I need, great. I'm done, and I'll send that back to the coordinator. What if I only find some of what I need? That's when it gets kind of cool. I could find nothing, or I could find like just a couple of the columns of a 6-column read or something like that. Well, then I'll read those out of that SS table, and I'll keep going back in time, looking in SS tables until I've assembled all of the columns I need from the partition read, and then I can be done.
Okay.
2 things here, and I'll kind of count these as for further research, and probably not good to dig into them here, but the compaction matters a lot here. This is why the smarts of the compaction strategy are going to try to ideally make it likely that all of the stuff I'm probably going to have to read is going to be in one place, because I don't want to have to go skipping around to 15 different SS tables to get me an answer. So I'm trying to avoid that, and the compaction strategy is our friend there. Also, there's a nifty data structure called a Bloom filter. Now, obviously, Wikipedia is the place you go for computer science questions, so you can get a great account there. I think there's also video of me at a OSCON, maybe in 2013. I think 2013, where I did a talk called "Data Structures You Need to Know." Where I get
perfect. We'll put that in the show notes.
If it's for real, put it in the show notes. If it's not for real, make sure everybody knows I talked about something that's not real. But I know I gave this talk at OSCON. I think the video's there, and I give a little.
Well, that's what a Bloom filter does, right? It tells you if something's not real.
It tells you if something is definitely there, or definitely not there, or probably there. And that's me. I'm saying it. The link is probably there. Go check. and that's what a Bloom filter does. It's an in-memory data structure that tells you you should look here. It's probably here, or don't bother. It's definitely not.
Mm-hmm. Okay. So, all right. I think we've talked about the read and write enough. Right? If I'm clear,
that's good.
I kind of lost. Okay,
there's always more to say, but that's the basic picture.
Absolutely. Yeah. So, okay. Well, you know what? You touched on this when you were discussing the write, and this is one thing that I find interesting about Cassandra is there's no leader node. There's no like name node type of structure. All of the nodes are somewhat created equal. And I want to get an idea for what are the characteristics of a distributed system that need a name node type structure versus a distributed system that does not need a unique node. Because, like Hadoop, for example, Hadoop needs a name node to orchestrate things. So what is this a question that you can answer?
I can talk about it. I mean, in the strictest sense, there's I'm being careful here. Hadoop, I think Hadoop could have been built with a without that reliance on the centralized name node. It was certainly convenient to build the system that way, and given the engineering constraints of Hadoop, it was right to take advantage of that convenience. So I'm not critical of Hadoop for having a single master name node. What you get for cheap with a single master is transactionality. And you can also probably make better latency guarantees within a certain scale, range of transaction rates. But you can get transactionality on the cheap in the ACID sense inside a single master. So that would be the first thing that comes to mind. If I really need ACID transactionality in my file system metadata, then let me put my file system metadata in memory. Well, I could put it on disk, put it in a single node, and I want it to be fast, so I'll put it in memory, and then out pops HDFS, right? With a system that is distributed in the way that Cassandra is, an architecture like Cassandra, you don't get ACID transactional semantics. Now, there is a feature called lightweight transactions that can, within a given partition, can give me atomicity. And I already had durability. You don't get isolation, but you can get atomicity, consistency, and durability. So you get 3/4 of ACID inside of lightweight transactions. So that's what comes to mind when I think about that question.
Yeah, no, that's a very interesting answer. Okay,
did you have an answer in mind? I'd be interested to hear what you were thinking.
I honestly I don't actually, but the next interview I have another interview today with Mike Caffarella, so I might actually ask him that same question.
Yeah, I'm interested to know.
Yeah. Okay. Well, so at DataStax, you work on Cassandra as a service. Why would developers want a service to manage their Cassandra rather than rolling their own? Okay,
let me back you up there a little bit. We actually don't have a Cassandra as a service product. There is a company called InstaCluster that is the Cassandra as a service company, and I believe they are an infrastructure partner of ours. So there's a loving relationship there between the two companies. They're great guys at Instacluster. They do Cassandra as a service, and that makes a heck of a lot of sense to me, in the same way that any as a service thing does, when I can handle the performance trade-offs of the service implementation in exchange for the reduced capital costs and reduced operational hassle and all of that. I mean, that makes a whole lot of sense. So as long as I can get that as a service thing, in EC2 along with my application farm or whatever, then it works great. And that's something like how Instacluster works.
Okay, sure. So I apologize for doing more research into Cassandra and less research into DataStax. But so what do you do at DataStax?
What do we do? I'll say what the company does, and I'll say what I do. And of course,
absolutely.
Now that we're talking about my employer, we have the safe harbor hashtag. Everything I'm saying is my opinion, and I'm not speaking for DataStax here.
Of course.
DataStax makes the commercial distribution of Apache Cassandra. We have a product called DataStax Enterprise, and we integrate analytics and search. That is code for analytics means Hadoop and Spark. Search means basically Solr, integrated with Cassandra. So you can do full text searches through a SQL query across indexed columns in a table. It's really amazing. And the Spark stuff is integrated Spark. So you've got basically Cassandra you could create data frames and RDDs from Cassandra tables and then persist them back into Cassandra tables. So that integration is there. It's also got other things like security that enterprises typically want. There's an in-memory feature. The management tool is way cooler in the enterprise version. It's kind of, the typical enterprise grade management stuff. The goodies like support and consulting and all that stuff. Those are really separate. DataStax is a product company. So that's that.
Sure. Okay. I would have loved to delve into that topic, but and maybe we can do another show eventually on that, as we talked earlier about Spark, and there would be plenty of interesting conversation around that. But I wanted to close off with some discussion around training and curriculum development, because you're heavily involved in this process of training engineers and explaining these types of concepts, as you've explained so eloquently in this episode. So you're working on a modular curriculum system to improve this type of training, this type of enterprise training. Tell me more about that curriculum system.
Absolutely. And that's, I said this in my introduction, that's really what I do at DataStax. I'm the director of training. So I run a team that makes curriculum, which is the stuff you're talking about. And I also run a web team that makes a site called DataStax Academy. So we had the safe harbor hashtag, now for the shameless plug hashtag. That's academy.datastax.com. Cool. Training on open source Cassandra. It's not all focused on our product. So there's lots of stuff you can learn about Cassandra on that site. The curriculum system, so excited about this. So historically, enterprise software company like DataStax is going to have a training effort and curriculum and everything. And we all know the tools that gets built with, right? It's PowerPoint. You'll write lab procedures up in Word and maybe go to the trouble of exporting them as PDFs, and you'll have all these things to deliver. And that's kind of where you live. There's a number of reasons why I didn't want to do things that way, but the biggie is this. So about a year ago, we took a step back. Some people at DataStax who know Cassandra really, really well took a step back, and they built a mind map of all of the things you should know to be good at this. They were like, imagine the apotheosis of the Cassandra expert, the perfect Cassandra user. What would be all the things that person would know? Massive mind map. Like nobody's ever going to know that. But I said, all right, here's this tree, this graph of knowledge. And I said, all right, every node in that graph, every little topic in there looks to me like a little packet of curriculum. Like maybe that's 5 minutes worth of curriculum, or 10 minutes or so. If you made a video out of it, it'd be a little 5 or 10 minute video. And I got to thinking, okay, here's this big tree. every node is a little 5 or 10 minute topic. There's some slides, there's notes. You probably have some quiz questions and like exercises and maybe some test data and whatever stuff goes in there. It seems like, in fact, it doesn't seem like, it is the case that you could take that tree and map it onto a directory tree. It's a tree, you could put it in a file system. And so the path to a node in that knowledge graph is a directory path. And it seems like, gee whiz, here is this big project, and I could put this in a Git repo and throw it up on GitHub and collaborate around it that way. And you'd have this brilliant modular curriculum system. And this isn't a Cassandra thing. This is any topic. Build your mind map and go to town. Now, there are other problems you have to solve to make this work well. When you really get into building coherent courses with this, much more to say. But that's the basic genesis of the idea. And then I realized, PowerPoint, not really. Because then you can't control PowerPoint in Git. That's a disaster. And we needed a way to say, here's this graph of knowledge. Here's all these nodes all over the place. And it's all well and good to poke around and explore that on your own. But customers buy courses. They buy, give us the, operations and administration Cassandra course, or give us the basics course, or give us the data modeling.
Right, not the directed acyclic graph of information.
The graph's cool. There's a lot to say about the graph, but they want a course. And so it's like you have to annotate that with this other path through those nodes. Well, imagine each of those nodes is identifiable by a directory path. And so what we've built is we've built a little custom build. It's a Gradle plugin, which, if you know some of the stuff I've done, it should come as no surprise that it would be Gradle. And we'll just list those paths in a text file, and the build will suck in the slides and the notes and the exercises and all that stuff. They're all written in ASCII doc now, so the build is able to deal with them programmatically and gloms all those together into a packaged course. And you get a little zip file you open it up and you open the index HTML, and it says, okay, here are all your modules in the course, and click here for your exercises. And it's this nice web-based package.
Okay, so that makes a lot of sense. It sounds like a really cool project. And you're going to be doing some training at Strata plus Hadoop in March. Are the resources that you can create from this curriculum system, will they be utilized in your training there?
That is correct. They will. It is our plan as of right now. Let's see, today is the 18th January. Yes, it is our plan as of right now for all of that training to be delivered from this new next generation curriculum. My team's in the process of rebuilding and modernizing and bringing content up to date and porting into this new system all at the same time. So should be the case that all this is the new stuff, and we'll be able to distribute that web-based content as a zip file to anybody who comes.
Great. Well, that seems like a good place to close off. Tim, thanks for coming on to Software Engineering Daily for a really illuminating discussion of Cassandra. I hope the listeners will check you out on your YouTube videos or at Strata plus Hadoop in March. Thanks for coming on, and you're welcome to come on in the future if you want to talk more about DataStax.
Jeff, my pleasure, and I'd love to be back. I look forward to it.